Now let's talk about the problem of uncalibrated stereo. So here is the scenario. You have a monument of some sort, a three-dimensional scene, and you have two pictures. We'll continue to call it the left and right views. Two pictures of the scene captured using two different devices, perhaps two different smartphones. And now the problem is to actually compute the three-dimensional structure of this scene from these two pictures. So what we're going to assume here is that we know the internal parameters of the two cameras. Just to remind you, the internal parameters are the focal lengths fx, fy, and the location of the principal point ox, oy. We're going to assume that this information is available to us in the case of each image that we use. Now, this is not an unrealistic assumption. You can either calibrate the camera that you used, or very often, in the image itself, there is something called the meta tag, information that is embedded at the top of the header of each image, and that information often includes the focal length that was used, the f number that was used, etc. So all the information related to that particular camera, the intrinsic parameters, can often be recovered, extracted from the meta tag itself. So in any case, we're going to assume that the intrinsic parameters are known for this camera, and possibly being two very different cameras. And what we are interested in finding to calibrate our uncalibrated stereo system are the extrinsic or the external parameters of these two cameras, which essentially means the relative position and orientation of one camera with respect to the other camera. These are considered to be unknown. And that is our problem. The first step in uncalibrated stereo is to calibrate the uncalibrated stereo system. So now let's take a look at the main steps involved in uncalibrated stereo. Here is our scenario. We have a three-dimensional scene and we have our two cameras. For convenience, we'll just call them our left camera and our right camera. The left camera has a three-dimensional coordinate frame which is situated right here at OL. Right camera has its own frame at OR. Remember, we don't know the relationship between OL and OR. What we have at our disposal are these two images, and in these images, points are measured in terms of pixels, in the left image and in the right image, and that's given by U and V, the image coordinates. So as we mentioned earlier, what we are assuming here is that the camera matrix or the intrinsic parameters of each camera are known to us a priori. So that's known. And our first goal is to find the external parameters, in particular the relationship between the 3D coordinate frames of the two cameras, right here, the rotation and the translation. To do that, what we first do is find a small number of reliable correspondences between these two arbitrary views. That's easy to do. If we've actually taken pictures of the same object, you can apply something as simple as SIFT and find very robust matches, and those will serve as our initial correspondences. It turns out that for our calibration process, we don't need too many of these. We need a minimum of 8 matches. So those are the ones that are being shown right here. So once you've done that, then we can find, using those small number of correspondences, you can find the rotation and translation of each camera with respect to the other camera. So we can find the relative camera position and orientation, and we'll call that translation will be T, and rotation is R. Those are shown right here, translation and rotation. Now, once we're able to find T and R, essentially this uncalibrated stereo system is now been calibrated. And we go ahead and, using that information, find dense correspondences. That is, ideally for every point in the left image, you want to find where the corresponding point lies in the right image. Turns out once you know the rotation and translation, that turns out to be a 1D search, a search along a single line in the other image. So using that technique, we then find dense correspondence map, and once we have that, we can use these corresponding pairs to triangulate and find the location of points in the scene, and that is computing depth.